can keep this here. Wait. Go to the kitchen there. Do you know where are the spoons and forks kept for this? Okay, Max, so just go in the kitchen, one of the shelves, bring the forks and spoons for this. Should we start? Is everybody online? Can you guys hear me? People who are online?
Yeah, we can hear you.
So I think we're going to start in a minute. Let's wait for a minute and we can start. So I'm going to be presenting today my research topic, which is brushless Doubly-Fed reluctance machine. And I'm going to be presenting. I'm going to be presenting this in ECC, which is next month. The conference was supposed to be held in Vancouver, Canada. Unfortunately, now the conference is all virtual. I had booked my tickets. I had made a flight reservation, everything. But now the conference has completely moved online. And I don't think anybody else is presenting at ECC from our group this time. So this is one of the most popular conferences in our research group. And yeah, every year there used to be a lot of people going for this conference, but unfortunately, I think this year I'm the only one presenting from our research group. Okay, I think we can get started. Hi everyone, my name is Shivang. I'm going to be presenting on modeling of rotor flux barriers in a brushless Doubly-Fed reluctance machine. And I've done this research with my colleague Hadi Chaudhary, as well as my advisor, Dr. Arijit Banerjee. So far, prospective drive architectures have focused on single port machines, which basically means that all the power processed by the motor has to be processed by the power converter as well. So let's say you have a 1 megawatt motor. All that 1 megawatt of power have to be processed by this power converter, because that's the only converter between your AC grid as well as your motor. And what we see is that for the single drive architecture systems, if we try to compare the weights of the motor versus weight of the power electronics, so this is a study done by NASA on turbo-electric propulsion aircraft systems. And what it indicated that the weight of converters actually dominated the weight of motors. So when we are designing the system holistically, we have to look at both the weight of motors as well as weight of converters. And that's why if we go for a Doubly-Fed machine, we can actually reduce the size of power converter. So what happens here in a Doubly-Fed machine is you have two windings, stator winding as well as rotor winding. Your stator winding is directly connected to the grid, whereas the rotor winding is connected to the same AC grid via this power converter. And now for a Doubly-Fed induction machine, the rotor only carries a slip amount of power. So your power converter doesn't have to be rated for full power application, for full power, but it's only limited to your slip power right now. Unfortunately, the power is delivered to these rotating windings via slip rings and brushes in a Doubly-Fed machine. And that's why for applications like turbo-electric propulsion application systems, you want to eliminate those brushes in order to in order to reduce the maintenance. So our objective basically is to find out a drive system which first of all can reduce the power electronic requirement, just like a Doubly-Fed machine, but at the same time also eliminate the brushes and slip rings so that we don't have to have that frequent maintenance, and the reliability of the system is also increasing. Fortunately, there is a motor called Brushless Doubly-Fed reluctance machines which fulfills both of these objectives. So in this machine, you have two stator windings, just like a Doubly-Fed machine, but now both the windings are on the stator. There is no winding on the rotor. So you have two stator windings. And since we don't want a direct coupling between these two stator windings, they have to have different pole numbers. If you put two stator windings of same pole number, they will directly couple with each other, just like what happens in a transformer. So in order to eliminate the transformer type coupling, we have two stator windings of different pole numbers. And now the question is, if you have two stator windings of different pole numbers, then how do you produce torque? And that's where this rotor structure comes into play. So you see this rotor structure. So here we have this reluctance rotor of another pole number, and the objective of this rotor is to magnetically couple the one stator winding with another stator winding. In a BDFRM, the stator which directly gets connected to the supply is known as primary stator, whereas another stator which is connected to the supply via power converter over here is known as the secondary stator. For the current study, I have chosen the primary stator as 8 poles, secondary as 4 poles. Usually, in a brushless Doubly-Fed reluctance machine, the number of poles on stator on your rotor is the addition of your primary pole pair as well as secondary pole pair. So you basically have 4 pole pair primary winding, 2 pole pair secondary winding, and here I've chosen a 6 pole rotor. So what's going to happen is this reluctance rotor, it's going to modulate the MMF produced by this 8 pole stator winding. And when this modulation happens, it's going to produce some flux density harmonics, which will have a 4 pole component as well. So that 4 pole component of flux density is now going to couple with the 4 pole MMF of your secondary winding to produce torque. So this process is basically known as the flux modulation, and it's commonly used for a machine like BDFRM. The amount of coupling between primary stator and secondary stator has a direct impact on the torque profile and can greatly vary among rotor designs. So depending upon how you design your rotor, the amount of coupling happening between these two stator windings can greatly vary. So, yes, yes.
That rotor is not 6
Yes, yes, yes.
For this audience, you might want to change that.
Okay.
So you don't drive the audience crazy.
Okay. Yeah, so here I've put in a 4 pole rotor, but actually it's a 6 pole rotor. I'm going to change this for the fun slide. Thank you. So the outline for today is number 1. So what we're going to do is we're going to look at the conventional approach of modeling the rotor. How so far, what is the conventional approach authors have been using, and what is missing from that conventional approach. Secondly, we're going to look at how can we improve that existing model. So the model which we have, how can we improve upon that? Last but not the least, we're going to look at how much is the improvement from the framework we are proposing. So let's look at the conventional approach to design a BDFRM, as well as look at the rotor structure what so far have been used. The most commonly used rotor structure in a BDFRM has ducts and barriers. So the iron, which is shown by this green shaded, this green region, is basically iron, and these are called as flux guides. The air, which is shown by this white, is basically your barrier. So the flux is going to pass through this one of these ducts, and using so far the authors have used this ideal ducts approximation. What that means is, so far the authors they will propose that they have infinite number of flux barriers of 0 width. So right now, practically, you will have finite number of barriers over here and over here. But ideally, what authors have so far used, they will assume you have infinite number of such barriers of 0 width. With that assumption, the flux entering through one of the guides will also pass through the second guide. I don't know why is there a second pointer over here. Yeah. So is there a mouse over there? Can you move the mouse? I think. Oh no. I don't know what's. Okay. So basically, the approximation with this ideal ducts is whatever flux enters in one of these guides should exit only through the end of the same duct. It cannot cross through these barriers. That's the approximation what has been used so far with this conventional approach. But when we look at the FEA and we notice this region over here, what we found out is that flux lines actually cross the barriers, and we have to account for this flux crossing along this area barrier along this air barriers, so that we can have a better estimate of the flux density as well as torque. This figure actually shows you how bad the ideal duct approximation can be. So on the left side, what I'm doing is, so we are providing some excitation to both the windings. We are looking at the air gap flux density along the air gap, and if you compare the analytical model with the FEA, both the air gap flux density as well as the torque, you can see there is a significant difference between the ideal duct approximation and what we get. So number one, if you look at the mean torque provided by the FEA as well as the analytical model, there is about 40% difference. And one of the difference, this pointer is coming again. I have no idea. Take 1 second. Let me see if. So if you look at the mean torque provided by the analytical model and the FEA, there is about 40% difference. One of the major sources of this difference is not accounting for the flux passing through those barriers. Secondly, the analytical model does not provide us any information about the torque ripple. You can see it's basically a flat line. And that's because the conventional approach ignores the stator harmonics. So how can we improve upon this existing model? So how can we account for a better mean torque estimation as well as also calculate how much is the ripple torque? So that's where we basically propose a new analytical model for a brushless Doubly-Fed reluctance machine. And this approach has been commonly used for a synchronous reluctance machine. So both the machines utilizes a reluctance type rotor, but in a synchronous reluctance machine, you just have one stator winding. In this motor, we have two stator windings right now. So ideally, your torque is basically a function of the instantaneous torque is a product of your air gap radius and your Lorentz force. This Lorentz force now has two components, the electrical loading as well as the air gap flux density. So if we can estimate the electrical loading, if we can estimate the electrical loading and the air gap flux density, we should be able to estimate the torque accurately as well. In order to accurately estimate the electrical loading, we are going to include all the stator harmonics present in both the primary as well as secondary stator winding. And if you look at the air gap flux density, that's basically the difference between your rotor magnetic potential and the stator magnetic potential. So if we can also estimate air gap flux density accurately, we should be able to compute torque in a much precise fashion as compared to the ideal ducts way. So what we're going to do is we're going to account for the stator winding harmonics, as well as we're going to account for the magnetic potential drop happening across the rotors. Can you change the slide? I don't know if it's working. There we go. Yep. So let's look at what happens when we include the stator winding harmonics. So right now what I'm showing you, we have again it's a simplified version of a BDFRM, and I've excited only my primary stator. And if we look at the magnetic potential of the stator or the MMF function, we can see that after including the winding harmonics, our estimation of magnetic potential improves as compared to without winding harmonics. So that's how we can, first of all, increase the accuracy of your stator winding harmonics. Secondly, how do we compute the air gap flux density? So as mentioned earlier, the air gap flux density is nothing but the difference of your magnetic potential between the rotor and stator divided by the air gap function. Now, how do we calculate this magnetic potential of the rotor in order to calculate B? So what we are going to assume, first of all, here is that iron is infinitely permeable, which means the stator, this Fs, which is the stator MF, so there is no potential drop happening across the stator iron. Secondly, another approximation we use is that outermost rotor duct potential is basically set to 0. I'm showing you this example which just with one flux barrier per pole, but we can use the similar method for multiple flux barriers per pole. So here, what's going to happen is I'm assuming that there's going to be some flux flowing from this rotor duct to this rotor duct as well. So we are not assuming that we are assuming that there is some flux passing this barrier. And by using a simple magnetic relation, a basic magnetic relationship, the difference between the magnetic potentials over here is given by the reluctance of this barrier into the flux crossing this barrier. Now, this flux crossing from point B to point C is the same flux, the flux crossing this barrier is the same flux crossing from point B to point C. And we can basically use this relation number 1 and relation number 2 to calculate the magnetic potential of the rotor. So here between A to B point, your magnetic potential is Fr0, and since it's the outermost, it is set to 0. From point C to point Z, from point C to point D, it is the same duct, it is the same rotor duct over here. So the magnetic potential here is also Fr0, which is set to 0. So the only unknown here we have is Fr1. So by using relation number 1 and 2, we should be able to compute what is Fr1. Once we have an estimate of the rotor air gap potential, we can compute the air gap flux density. And again, going back into the previous relationship, once we know the air gap flux density, once we know the electrical loading, we can accurately calculate what is the torque produced by this machine. Again, this I have only shown for one flux barrier per pole. If you have multiple flux barriers per pole, we have to use recursive iteration. I'm not going to show that in this slides because there's a lot of maths involved there, but we have proved that in our paper. Now, how much is the improvement once we account for the stator winding harmonics as well as the magnetic potential drop across the barriers? So here, what I'm showing you is the result with 2 flux barriers per pole. So we have put basically 2 flux barriers. The angle between A and B, which is called the half span angle of the first barriers, it's 15 degrees for this case. The angle between A and C, which is called the half span angle of the second barrier, is 24 degrees for the current example. And if we look at the flux density, the analytical model, the conventional one, the proposed one, what we have proposed, and the FEA, you can clearly see that the proposed model matches much well with the FEA as compared to the conventional idle duct approximation. We can also look at the torque, and now what we see is the mean torque now is definitely reduced from what was proposed by idle ducts. It's still higher than obtained in FEA, and that's basically because we still have not accounted for slotting effects in stator and rotor. So if we can include those slotting effects by using a Carter factor, this difference in the mean torque between the proposed and FEA can be accounted for. But if you look at the ripple torque, the difference between the ripple torque obtained in a proposed analytical model and FEA is less than 5%. So after we had recognized that, okay, that our model basically calculates the mean and ripple torque accurately or more precise as compared to the idle duct approximation, now we want to look at some sensitivity analysis. So what we are doing is we are changing the location of these flux barriers. So initially, if you remember, I had placed these flux barriers. So this angle A and B was 15 degrees, A and C was 24 degrees. So we can basically change the position of these flux barriers and see what happens to the mean torque as well as ripple torque. So I have 2 designs over here, design number A and design number B. The second flux barrier angle is same for both, it's set to 24 degrees, but you can see that between A and B, I only changed the span angle from 15 degrees to 21 degrees. The mean torque obtained is almost the same, but the ripple torque is more than double for design A as compared to design B. So what this graph basically shows is, unlike in an idle ducts approximation where authors used to place ducts wherever they wanted, it's not a good idea to do that. The location of your flux barrier highly impacts both your mean torque as well as ripple torque. So where you place your flux barriers have a direct impact on your ripple as well as mean torque. So once we know that, okay, our location of the flux barriers can impact the torque density of the machine, what we try to do here now is create an optimization problem and solve it using MATLAB. So the objective here is to maximize the mean torque, minimize the ripple torque under some decision variables. Since this optimization is carried for 2 flux barriers per pole, we have certain decision variables over here. The half span angles of the flux barriers, the thickness of the flux barriers, as well as what should be the stator excitations. So both the current excitations as well as what is the phase offset between those current excitations are kept as decision variables over here. And now since I have a control over stator currents, I should also constrain my flux density so that I don't saturate the machine. In this analysis, the constraint is basically put on the air gap flux density because we already calculated that, and we constrain that air gap flux density to a certain value. And the output is obtained as a Pareto front as what we expect in a multi-objective optimization is shown over here. One interesting point, what we observed over here was this was something we had done in our last research. What we showed was in a conventional approach, authors used to use same excitation of both the stator windings and keep the phase difference as 90 degrees between both the stator windings. So that phase offset is shown by this delta term over here. So conventional approach to designing a BDFRM was have equal stator excitations and make this phase offset between those 2 stator excitations as 90 degrees. What we had shown earlier last year was delta 90 degrees actually is not an optimized approach. Delta 120 degrees initially was a more optimum approach, but that was using an ideal dust approximation. Once we go away from ideal dust approximation, that delta 120 degrees or 90 degrees, the optimum design may be anywhere else. So here, as you can see, as we keep changing the delta, we are able to put more currents into the machine, and we are able to get more mean torque, but the ripple torque percentage also increases. So it's again a trade-off between mean torque and ripple torque over here. So right now I have chosen design C to show you the results. So this design C, which is the output of your Pareto front, is chosen for doing the FE analysis. And on the left side, we are basically doing the flux density. We are showing you the flux density distribution. And as can be seen that the flux density is limited to 1.5 Tesla, which was the core saturation flux density. We also did the stress analysis on this tangential iron rips over here. So while doing the analytical calculations, we had ignored the iron rips present on the rotor structure, but in reality you have this tangential iron rips, and we have to account for those while doing the stress analysis. And the stress found out here was about I think 168 megapascals, which was less than the tensile strength of around 400 megapascals. Similarly, for the chosen design C, this graph shows you the comparison between the conventional analytical model torque prediction, what we propose, the blue waveform, as well as the torque obtained in FEA. And on the right side, this is the Fourier transform of this torque profile. As we can see that the conventional approach estimates the highest amount of torque. The proposed model makes sure in the proposed model, since we account for the magnetic potential across the rotor, our mean torque estimation reduces. FEA torque, it's even lower than that. And this is because of the slotting effects which we have ignored in our proposed analytical model. And you can see that the ripple torque, which are the harmonics presenter 12, 24, 36, 48, is also given by the proposed analytical model. So with this approach, by accounting for both stator winding harmonics as well as the potential drop across the rotor barriers, we can have a good estimate of our mean torque as well as the ripple torque, which is crucial for designing a machine like BDFRM, because in a reluctance based machine, the torque ripple actually can go beyond 30%. And that's why we have to look at how we are placing the flux barriers and how it is interacting with the stator harmonics in order to reduce the torque ripple. With that, I would like to acknowledge 3M and Grinder CAME for sponsoring this research, and thank you. And I'm available for any questions right now. Yes.
I was about that. Can you go back to your Retor front optimization?
Yes.
So I know you're only showing 3 points here, but
Yep.
there seems to be a pretty noticeable trend in your delta versus kind of how your curve goes across.
Yep.
If you plot some of your different decision variables and the results of those Retor front optimizations, does it turn into something that looks more like a function and not something that needs a genetic algorithm to find the optimal for?
Can you repeat the question again? Sorry.
Yeah, so I guess you applied a multi-objective optimization.
Yes.
And you've got this Pareto front, but
Yeah.
at least based off the one variable you've shown so far,
Okay.
you've shown this very clear kind of what looks like a trend.
Yes.
Now, obviously, I don't know if that's the case for all of these points,
Mhm.
but if you start plotting out some of these decision variables based off of the Pareto optimal solutions to it,
Yeah.
are there, is it more, do you see more of a function among this, or
Okay.
is it just that you pick 3 particular values that show this trend?
Okay.
And it doesn't pull up the rest of the cases?
Sure. So what I know so far is, so right now I'm only showing you the one decision variable, which is the delta over here. There are several more decision variables over here, right? The how like where you have placed the barriers, what is the thickness, and what are the stator excitations. So what we found out, so this was the research we had done earlier as well, is if you use a delta of 90 degrees, which was a common approach using with the designer. So even in a conventional singly fed machines, we try to phase shift the rotor and stator flux density by 90 degrees so as to get maximum torque. Unfortunately, in a brushless Doubly-Fed reluctance machine, if you do that, you are limited by the peak flux density. So if your phase difference between the two stator windings is 90 degrees, what happens is you reach your flux density peak before you hit your current density limit in these machines. So what happens is once you start increasing the delta from 60 degrees to beyond 107 degrees and even more, we are able to inject more currents into the machine so that we are hitting both our current density and flux density limits at the same time. So what will happen is I have not shown the current values over here, but if I go from point A to point C and beyond, this currents IP and IS, so basically the primary and secondary current, their values are also increasing, and that's why we are getting more torque out of the machine. But the peak flux density between design A and design C is still the same. The remaining variables, the angles, thickness, their solution is a bit more complex, and it's not a simple function. Are there any questions from the online section? Okay, thank you then.
Can everyone hear me? Hello?
Yep, we can hear you.
All right, thanks.
Slideshow.
And so, hi everyone, I'm Adriano Abrantes, and today I'm going to be talking about battery energy storage systems and their operational flexibility impacts in grids with a lot of renewable resources. So this is the outline for today. I'm going to quickly go over introduction and motivation, then mention battery degradation, costs, representation as variable operational costs when we're trying to decide how to operate the battery in electricity markets. And then we'll talk about the model of battery energy storage systems in markets, and a few case studies, and then we draw some conclusions from those case studies. So as we have more renewables in the grid, we have more challenges trying to keep supply and demand equilibrium at all times. I think most of us are familiar with the curve phenomenon. When you have a lot of PV, you can have negative prices during the day because you have a lot of slow resources that you're going to need later on when the sun is out. So you cannot turn them off, but they have minimum output limits. So they have to stay online, and the operator is basically paying consumers to consume electricity so that we don't have to turn off a large unit that's going to be very expensive or maybe impossible to turn on back again at 7 or 8 p.m. And so storage can provide the additional degree of freedom that the operator needs to solve this problem, right? So when there's too much sun, there's not enough load, the storage can charge for free or perhaps even get paid to charge, and then discharge once the sun is out. And there's a huge ramp that a lot of typically gas-fueled resources need to ramp up to meet. So many times, since the controllable resources cannot ramp fast enough, what the operator needs to do is curtail that renewable energy during the day so that that ramp is not that bad. And so one of the things that storage can do is prevent that renewable curtailment. And once you have the peak load after the sun is out, the operator typically in a day when the load is high, the operator may rely on very expensive and polluting peakers that are turned on a few times a year, but still have a very high cost and also have serious emissions. And so batteries in markets, right? They're profit-seeking participants, and they typically will profit. Nowadays, they mostly profit from ancillary service provision. So they provide frequency regulation, and they can provide reserves. And so they can do this without having to charge or discharge their batteries too much. And so it's a very steady revenue stream, but it's not that significant. And we hope that storage can actually provide bulk energy at time need. And so another way that storage can benefit and can profit from is from energy arbitrage, for buying energy when it's cheap and selling it when it's expensive. So buying when the system has a lot of it, or maybe even too much, and selling when the system is going to need to turn on expensive resources to provide that energy. And the thing is, once you look into how to use these batteries, you realize that if you're going to discharge a battery significantly, there will be a lot of degradation to the battery health, and you're going to decrease its lifetime, its useful lifetime. And even though battery prices have been decreasing significantly, that's still a very significant cost of operation. Simply to do a discharge, if you discharge your battery to a very low state of charge, there's going to be a replacement cost associated with that. And if you ignore that, then you, as the battery market participant, you may make a lot of money in a few months, but you have to replace your battery soon, and that will be very costly, and you might end up with uneconomic operations. And once you start looking into degradation models, it can get very complex, and you may reach models that it's really hard to build some scheduling problem on top of it. So in this presentation, what we did was focus on lithium-ion technology. It's the type of battery that's been most applied in the last 5 years in the US. It has high energy and power density, low self-discharge, and the costs have been decreasing very quickly. And we use a simple model that is based on the depth of discharge. So if you have a battery that's at state of charge, it's 0.5, right? And then you discharge 0.05, and then you charge again 0.05. Then you did a cycle that the depth of discharge was 0.05. And so that once you can actually measure how deep the cycles you performed are, you can estimate how much life your battery lost due to performing these cycles. And we take the data from this study where they took a specific type of lithium-ion battery, and they saw how many this equivalent full cycle you can see as a measure of energy, of how much energy you can charge and subsequently discharge on the battery, from the battery, charge to the battery, how much energy you can use it, right? So say that your battery can store 1 megawatt hour, an equivalent full cycle is going to be 1 megawatt hour. And so this is saying how much energy you were able to charge and subsequently discharge and then charge again to the battery, the charge throughput of the battery. And on the horizontal axis, we have the depth of the cycles in which you did discharging and discharging. We can see that, for example, in the purple curve, where we have the average state of charge to be 50%, and we have even a point of like the depth of discharge to be 100%, you can see that this battery can withstand something around 400 cycles, full cycles, and then it's going to lose its capacity, and it's going to be dead. You're not going to be able to apply it to the bulk grid anymore. And so it is much more profitable for you to perform the 8,500 cycles at 5% depth of discharge than to perform deep cycles at 100%. And so what we do over here is we check whether the battery, once it's performing following a specific charge discharge schedule, how deep are the cycles it is performing, and we associate the loss of life of the battery according to the depth of these cycles to a dollar value based on how much it costs to replace the battery. And so now that we talked about having the degradation represented in the, once we're trying to schedule how battery is going to participate in the market, I have to talk about the rules for batteries participation in the markets, right? So we have FERC order number 841 that established that grid operators must enable storage to participate in markets either through bids and offers or by self-scheduling. So typically, a market participant doesn't have complete awareness of the market. So especially for a battery who's not a market participant, like a generator that has incentives to submit offers based on their marginal cost of operation, the battery is trying to maximize profits based on arbitrage. And so they'll use price forecasts to determine how to bid or how to schedule themselves. And very often in the literature, you find that sometimes even implicitly that battery market participants are assumed to self-schedule. They have some knowledge of the prices, some information on the prices, and they tell the grid operator how much they're going to be injecting to the grid and withdrawing from the grid at each time. But this approach has several shortcomings and may be inadequate to represent battery storage in markets and in any kind of simulation study. And there are many reasons for that, but if you think about it, a self-scheduled resource you cannot set the price at any time. It enters the market optimization problem as simply a constraint. That resource is going to be injecting that amount or withdrawing that amount at that time, and there's nothing the operator can do about it. And once they've decided that schedule, it doesn't matter if the price turns out to be very different from what they thought it would be. They're going to have to perhaps pay to inject or withdraw during very high prices. So there's no price responsiveness. Once they decide this, their schedule, they're going to have to follow. And there's also the issue that from the grid operator's perspective, it's just something that was decided by a third party that, oh, that resource is going to be doing this, and they have to deal with it. It doesn't give the main benefit of storage, which is to give the grid operator some flexibility, the ability to use that storage in a convenient way for the whole system. And in addition to that, typically when we're solving a market problem, we're trying to maximize social welfare. And so each customer, right, each buyer and each generator, they have a contribution to the social welfare. But once you have any resource participating as a self-scheduled resource, it doesn't show up there. And you can even look at it as some sort of around the market type of operation. Now, once we have bid-based battery operations, then the battery can actually set the price. So we can offer energy at a price, and that becomes the price that the market clears. So in that situation, it's very likely that the battery will be attaining profitable operations. And once it's determining its bids, it's considering various possible dispatch schedules. And for each possible price realization, those bids are going to lead to a different schedule. And so we say that this dispatch schedule of the batteries is price responsive. And so it's very unlikely that the battery, the market participant, will have an economic operations, because if the prices turn out to be very different from what they expected, well, their bids will just not clear and they won't lose money trying to serve the grid. And if they considered that, oh, maybe there will be a price spike today at this hour, and they included in their bids a very expensive block, then it's a low probability price deviation that they can profit from. And this doesn't really affect how they would operate if the price spike didn't occur. And again, once you have bid-based battery operations, then the grid operator can decide how to use those batteries, and the bids will guide the operator to decide how to do it in a cost-effective way, and will enable the reduction of curtailment and the use of expensive and polluting peakers. So when I'm talking about the scheduling problem, the self-scheduled storage resource, this is the kind of problem we're looking at. Say you consider various possible price realizations. Over here, price is denoted by lambda. And so you consider price scenarios. The letter S represents a scenario. And we're trying to here maximize the expected profit for the storage resource. So for each scenario, we're trying to get the maximum of the price times how much energy we inject, which is G, minus how much energy we withdraw, which is L. So how much we get from the energy we sell and how much we pay for the energy we buy, subject to the operational constraints of the storage resource. So this is not talking about a battery specifically, just a generic storage resource. And the U variables here say whether the the storage is in the charging mode. So UL is charging. When UL is 1, the storage is charging. When UG is 1, the storage is discharging. And if both are 0, the storage is idle. And it's simply keeping energy to use for a later time when you can profit more. And we have limits on how much you can charge and how much you can discharge on constraints 3 and 4. and constraint 5 represents the energy rollover. So the energy you have at a certain period is the energy you had in the previous period times how much you charged or discharged, and taking into account the charging and discharging efficiencies. And you also have limits on how much energy you can store. And you typically have the last constraint where you're saying that you want to end a specified scheduling window with at least or with your energy within specific bounds. So you're not making myopic decisions. For example, you're not ending the day with absolutely no energy, even though you know that you could sell that energy in the beginning of the following day or something like that. The problem with this is that if we look at the objective function, you can rearrange the terms as in the bottom equation, as in the bottom statement, and you see that what you're doing, in fact, is just trying to decide a schedule, so the G minus L, based on the expected price profile, which is the term under parentheses. And so any deviation that of the price that actually happens from the expected price profile is likely to make your operations suboptimal. And once we propose the bidding problem, we are actually trying to bring this price responsiveness into the problem. And so we pose the EBP, the energy storage resource bidding problem, as a two-stage stochastic optimization problem. And we solve this all at once as a single mixed integer linear program, but it's two-stage in the sense that we separate the variables into the here and now decision variables, so what we need to decide, and that doesn't depend on a specific price scenario. We need to decide what bids we're submitting and when we're going to be in charging mode or discharging mode. Now, once we've decided that, then we have, well, what happens now, right? So you submitted these bids, the price is this, so you'll get some bids are cleared, some are not, and based on that, you know how much you have to charge and discharge at each time and what's your resulting stored energy level. So we solve this problem altogether, but that's where this term two-stage comes from. And now the objective function looks like this. And the only difference is that now G and L depend on the scenario S. So for each price scenario, our bids are going to be cleared in a different way, and we're going to get a different dispatch schedule for the storage resource. And so we're not simply choosing a fixed schedule that will try to maximize profit for the expected price, but for each price scenario, we're trying to choose an optimal schedule as long as the bids we come up with can accommodate those distinct schedules for those distinct prices. So this is the main thing that we take from the bidding problem, which is the in this case, a demand bid curve. It could be also a supply offer curve. Here we use pi to denote the prices of each energy block, and the quantity that we offer in each block is delimited by the betas. And so when we solve this problem, we choose the betas and we fix them, but we can have a very large number of betas so that this curve can be very fine. And once we determine this curve, if the market has a limit, say most markets can only accommodate 10 blocks in a bid, we can adjust this so that the resulting curve is within the market requirements. And we can even do that within the optimization problem. So we take this as a constraint and still get an optimal curve, given that we can only get 10 blocks, 10 distinct prices. And so we were talking about this generic EBP, but for batteries, we introduced battery degradation costs in the objective function so that we specify bids and we take those degradation costs into account along with price uncertainty. And this is especially relevant for batteries, that we specify dynamic energy limits, so energy limits that are changing over time for the battery base, for the BSS EVP, for the battery bidding problem, because once our operational costs are so dependent on the depth of the cycles, if it turns out that the prices led for a much deeper cycle than what you were predicting, you may attain uneconomic operations. However, FERC Order 841 specified that in their bids, storage resources can also include information about their energy limits, dynamic energy limits. And so we take all those possible stored energy level values over time that we get in the bidding problem, and we make sure that we use their maximum and their minimum as limits in our bids so that we don't run into uneconomic operations. And so we ran a few case studies with this test system. This was a test system developed by Agrawal, and they have taken solar and wind data from actual geographic locations, and the line parameters were based on real systems, and they're trying to fit this into a real terrain in the US. But so this is a fictitious grid that tries to be realistic, and it is based on the IEEE reliability test system with some modifications. And what we've done with it in the first case study is, well, we run the system without any storage. We get prices for the whole season of spring. And then once we have those prices, we use them as scenarios to represent how a storage resource would operate in the grid at a specified location, and evaluate what are the contributions of the storage to the grid, or how the storage perform based on its profits. So when we run the system without any storage, these are the prices we get. Each color here represents LMPs, LMP profiles, price profiles for Spring Friday. And we have in gray, in a thicker line, the average, the expected price for every Spring Friday in our study. And we use these scenarios as inputs to the EVP. And we also solve the self-scheduled battery problem so that we can compare so that we can compare their performance. And so over here, we are showing the resulting schedules for a 50 megawatt battery storage resource that can store up to 50 megawatt hours. We considered a battery replacement cost of $135 per kilowatt hour. And the charging and discharging efficiencies are both 0.95. And the bids and offers can contain up to 10 blocks. And so we're showing the prices again, just so you can see how they are aligned to the stored energy levels in the bottom plot. So in the bottom plot, we're showing in blue the prices for that particular Friday, and in red or in magenta, we're showing the stored energy level, and the dashed lines are for the self-scheduled battery, and the solid lines are for the bid-based battery. And so we can note that the self-scheduled battery charges at hour 4, which is a local minimum of the price in the early morning, and it discharges at hour 7, which is a local maximum of the price for a Friday in the spring. But because the BSS discharged at hour 7, the price peak that it was expecting to see didn't occur, and in fact it occurred in the hour right before that. And so the BSS participation as a self-scheduled resource affects the prices very significantly and makes it harder for the BSS to profit from operations. And you can see again that the self-scheduled battery charges at hour 13 very suddenly, simply because that's the lowest price in the day for the expected price profile. So everything that the self-scheduled storage resource is doing is based on the expected price profile. And finally, it discharges at hour 19, right, because that's the highest price of the day. But it turns out that for this day, the price peaked at hour 18. Once again, 1 hour right before the self-scheduled storage resource decided to discharge 20% of its energy. And the reason why it's doing only 20% is that if you do cycles with this degradation model beyond 20%, you need a price spread of more than $200 per megawatt to justify. And we don't have those kinds of prices in the system. So we never see either the bid-based or the self-scheduled battery going beyond performing cycles deeper than 20% of their SOC. Now, the bid-based battery, it discharges slightly less at hour 7. But when it's doing so, it is the price setting resource. And that's why the price over there, you can see it stayed around $100 per megawatt hour. And during the day, from hours 10 to 14, the bid-based storage resource is charging slowly, making sure that it will only charge at a very near zero price. It's not simply charging at hour 13 because that's the expected minimum, but it's charging throughout the periods as long as they are in fact very low priced. And then we can see through hours 18 through 20 that the bid-based storage resource, the battery, is discharging. So it didn't discharge all at once at hour 19. And in fact, it was the price setting resource in all these 3 periods. So you can see that the price is relatively high. And at hour 19, the storage discharges a bit less and the price is a bit lower. And so if the price were higher, you would probably have seen the storage discharging faster at that point. And so once we take all the results for the whole spring season and compare the self-scheduled battery against the bid-based battery, we can look at this plot where we're taking the average daily amounts for energy revenues, reserves revenues in dark green, degradation costs in dark blue, energy charging costs in orange, and net energy profits in light blue. So by net energy profits, I mean it's the revenue minus the charging costs minus the degradation costs. So in fact, for that day, the storage, the BSS market participant will have more money than that, but we're assuming that that dark blue part is something kept aside to replace the battery due to the cycles it performed for that day. And so we can see that for the 50 megawatt battery, there's a small difference between their performance, but already the bid-based battery pays less for energy and has less degradation costs. And once we increase the size of the battery, this profit difference tends to increase. And the major difference is with respect to the degradation costs. The self-scheduled battery increases its degradation costs significantly. Sorry about that. And while the bid-based, no, the bid-based keeps spending very little money on charging costs and discharging the battery less. So it's in fact using the battery slightly less, but it's still attaining more profitable operations, as you can see in the light blue bar. And one thing that, I think that's a very important thing, that the self-scheduled resource tends to overuse the battery and have less profitable operations. We can see that going from the 200 megawatt to the 400 megawatt battery, there was barely any difference in the average daily revenue for the self-scheduled resource, while for the based resource, we still have a significant increase, even though it's not doubling and we're already having a lot of storage in the system so that it becomes harder to profit at the same ratio as before. And so the other case study that we ran, I guess I'm out of time. We evaluated the impacts of battery operations into the same test system, considering 3 scenarios where we have PV installation capacity going from 1 to 3 gigawatts, and we considered 3 battery sizes, 50, 100, and 200 megawatts. This is a typical weekday load and generation profile. So we can see that the battery is charging throughout the hours that the sun peaks, and the battery discharges at hours 6 to 8 when the sun is just out and peakers would be needed to meet the load. The main takeaway from here is that as we increase PV installed capacity, we increase the BESS profits. And in fact, you can have a larger battery once you have more PV in the system. Otherwise, if you don't have that much PV in the system, the battery doesn't profit that much additionally, even though it's double or 4 times the size. And here we can see the daily CO2 emission reductions. And again, right, for not that much PV installed capacity, it doesn't matter if you have a 50 or a 200 megawatt battery in the system, and we're talking about 10 of these batteries spread throughout the system. But once you have a lot of PV, then having more storage makes a significant impact in emissions. And also here for renewable energy curtailment reduction, right? Once you have small PV, you barely have any curtailment at all. And once you have 2000 megawatts, you have curtailment, but you can see that the 100 megawatts batteries are already sufficient to reduce it. And as you have more, you can actually start thinking about having more storage in the grid, and they will be able to provide the flexibility needed to accommodate those renewable resources. And here we're talking about startup costs. And again, once we have more renewables, we can achieve high reduction in the startup costs. And that really goes along with the curtailment reduction and the emission reduction. So, but to summarize, we compared the bid-based and self-scheduled BESS operations. We could see that the BESS bid-based operations were 80% more profitable on average than the self-scheduled one. And if we had more time, we could go over the studies showing what happens when you have 10 self-scheduled batteries, and they typically tend to do the same thing all together, and that could actually become a problem for the operator. And you have the BESS and renewable energy resources, their operation complement each other, and you will be able to have more BESS as you have more renewables in the system, and vice versa. And we could see the effects of BESS operations to reduce startup costs, to reduce emissions, and curtailment. Sorry about taking too long.
Any questions? Okay, I must thank both of you for presenting. Very nice seminars, both of them. Thank you.
Hey, George, can I ask
Yes,
a
sir.
question?
Yes.
A suggestion for Adriano would be really useful maybe to present some of those financial results on sort of a per unit basis. I mean, it's really hard to tell whether $3,000 a day is a lot of money or little money, you know, with respect to the system size. I mean, you can sit here and do the back of the envelope calculations, but it'd be nice to have it in the paper.
Well, it bothers me with those results, Phil, that that as you increase the size on a per megawatt basis, you're decreasing your profits. So there's absolutely no incentive not to have 450 megawatts units as opposed to having a 200 megawatt unit.
Right, right. So, you know, some of that analysis needs to be kind of built in. I guess the other thing that's really hard to tell there is that it looks kind of, even in spite of what you just said, it looks a little bit pessimistic for scaling down.
Yeah, well, I know that we need more capacity, but it seems to me that if we put in 450 megawatt units, we should be able to maintain that unless they start competing with each other. Because this lack of economies of scale in terms of profits is a little bit disturbing. I mean, why would you go and spend probably 4 times as much for the investment and get not commensurate amount of revenues from that?
Certainly, certainly. Okay, thanks.
Thank you, Professor. And there's also an aspect that I'm looking into. I'll definitely try to put these numbers in a per unit basis, even though they won't look that promising. But we're also looking into a few flow battery projects that have been announced to start to actually be constructed. So we can use those prices and take this degradation model to a different level where it's not such a big impact, so that we can actually use something like 90% of the storage capability instead of just 20 as we have now with the lithium batteries.
Yeah, I think that would be good to get those presentations, because I think that would make sense to get that, Adriano. Okay, thank you, everybody, and see you next week. We're again going to have dual tracks. Next week, we will be meeting in 5070, and also you can catch us by Zoom. So thanks very much for your participation. Adriano?
Yes.
If you have a few minutes, can you just ding me? I want to go over some of the slides.
Okay, thanks.
Thanks, bye-bye.